Awesome, there we go. Okay, so we just have a little bit left to go through. We did ionization energy, electronegativity, and then I believe briefly electron affinity last time. So yeah, all we've got left right now is the chemical activity and the oxidation states. Let me go ahead and pull up our blanks here. So, when I say chemical activity, what does that mean? What does that mean to y'all? Any clues? Word means nothing. It's just words on a piece of paper right now. That it? That it? Okay. Well, when we talk about chemical activity, we're talking about how reactive a metal wants to be, how reactive it is essentially, right? So metals and nonmetals are going to have different requirements for being reactive because a lot of times those deal with the electrons in those metals or nonmetals, right? So if we're starting here, metals tend to blank. So I didn't put a blank here. I should have put a blank there. So do metals oxidize or reduce? Mainly they want to oxidize, right? Because with oxidation, what happens to a metal? Do they gain or lose electrons? They lose electrons, right? And so what side is the metal on? What side are metals on the periodic table? Left side, right? So does it make sense that they want to lose electrons to get back to noble gas state, right? And traditionally as well, even in the transition metals, vast majority of transition metals, when they form ions, they'll form cations. They'll form positive ions. There's a few that'll form anions, but not as many as would form cations. So generally metals want to lose electrons, which means they want to be oxidized, right? So what would make an electron easier to remove off an atom?
Lower binding energy.
Lower binding energy, right? So if we're talking about like any other reasons that it might want to lose an electron, or what would make it easier to lose an electron? Yeah, feel free to look back at your notes too to try to think about it too, because I mean a lot of the same reasoning is going to be applying here too. So we know that, like Cooper said, lower binding energy. Lower electronegativity, that's another one. That kind of goes into lower binding energy as well, right? Because it's more loosely held, right? So it makes it easier to remove. Is there another way that would make an electron easier to remove? Like, what would make it less tightly held to the nucleus?
The type of orbital, type of sublevel.
Type of sublevel? Maybe. I would say the size, right? Because I mean, if it's further away from the nucleus, it's way easier to remove, right? And that goes back into like again the lower bonding, or the lower nuclear charge, right? It goes into that because it's less tightly held there, and it's less tightly held farther outside. So not only is it going to be less tightly held if you have a lower nuclear charge, it's also going to be less tightly held if it's way farther away from the nucleus, right? Does that make sense? So, with that being said,
Don't forget we have that video.
we do have that video. I'm pulling it up so we can fill the notes and we'll show the video.
You can do it. Come on, you can do it.
See, I got so good at it. Now I can't do it anymore. There you go. And let me erase the rest of this. So then let's try to fill these in then. If we know everything that we just said about what makes an electron easy to remove, which by the way, let's go ahead and fill in this first one. Metals tend to lose electrons. Right? So if we're moving down in a group, would the chemical activity of the metal increase or decrease? Decrease? Okay, so here increase or decrease. So justify Why do you think it's decreased? That's a good question. Cooper, why do you think it's increased?
Well, I think it's decreased because the more, or the further you go to the right, the more electrons it has.
No, not further to the right. From move down a group. Down a group.
Oh,
Yeah.
I have no idea.
Increase because like they get bigger. You said that.
Yeah.
Because if it's going to get, the bigger it is, the easier it is to lose electrons.
Yeah, so the bigger it is, the easier it is to remove electron, right? Which would make a bigger metal here more reactive. Because, again, metals want to lose electrons, so the more likely something is to lose an electron, the more reactive it's going to be, because it's going to react with way more substances, way more violently, because it's way easier to remove that last electron, right? Which I guess this kind of makes, does that motion make sense to y'all? I'm just kind of doing it as a way to show, but yeah, so it definitely increases. And so you said just the electron gets bigger. Yeah. So yeah, that's exactly what we said here. The wording in the notes itself is that atom gets bigger. Therefore, the valence electrons are less tightly held. By the nucleus. So that's the official wording. It's pretty much exactly what you said though, Sam. Essentially, if the atom gets bigger, it's less tightly held, which means it's easier to remove. That's a simple way of explaining chemical activity, right? What about from left to right? Does chemical activity increase or decrease?
Decrease.
Decrease. Alright, so we're all in agreement there, right? Why does it decrease?
Yeah, I'm
You're
getting
gonna get
smaller.
And also, they're not metals as you move move with the field.
Yeah, so they're not metals as you move from left to right. Atoms going to get smaller, but what else increases as you move from left to right? Electronegativity, or what have you been using to justify?
First ionization.
Not, well, so those are all true, right? But remember, the reason those happen is because of the effective nuclear charge inside, right? Because there's a stronger positive charge acting on the same energy level, right? So it ends up overall, that's one of the reasons why you decrease in size, but it's another reason why it's harder to remove those electrons. So essentially the trends are the same, and it's essentially that justification justifies it going small, the effective nuclear charge justification justifies, how it's getting smaller, and you can use both to justify the fact that it's harder to remove an electron, right? So, but we'll use, either or is good for B if you want to fill it in. With notes, I just use atoms get smaller. But all of it follows the same strength. They acknowledge they get smaller, but now you know how to justify why they get smaller again because of that nuclear charge acting on that entire energy level. Therefore, the valence, I guess this is supposed to be electrons, so I'm just going to do that. Fill the last part nucleus. Alright? And so that's your trend from here with chemical activity with metals, right? So we can go through and do non-metals real quick. Y'all see that fairly well. I kind of shifted this all over, but make it a little easier, especially for the video to see that non-metals part too. Okay, so non-metals tend to gain electrons. So if we're gaining electrons here, what would make it easier to gain electrons? What makes an atom more likely to gain electrons?
Being, small, because it holds them in.
So yeah, being smaller because the atom holds electrons more tightly, which means there's what that's happening. So what's the nucleus? Is it stronger or weaker? It has a stronger pull for electrons, it's a stronger effective nuclear charge, which means it's got a stronger attraction for any electrons that would want to be added to it, right? Alright? So, chemical activity then for going down a group, does it increase or decrease? I heard, what'd you say?
For A?
Yeah, right here.
Yeah.
Yeah,
Decrease and I heard increase, alright? So, why decrease? Madison?
because it's the opposite of chemical activity.
So it's the opposite of metals though, right? But like, what's the specific reason, right? Like, so remember what we're saying is that nonmetals tend to gain electrons, right? And so what happens to the atoms as you go down a group? They get bigger, right? So if they get bigger, is it easier or harder to get or for it to gain electrons?
Harder.
It's harder, right? So, because, again, we can actually talk about the shielding here, right? Because remember, with an effective nuclear charge, and you have atoms here, let's say for like hole shielding, you've got the strongest nuclear charge, let's say we're working with like, I don't know, iodine, right? So you have this giant nuclear charge of 53 in the middle here, but you've got this shell 1s, and you got a 2s shell, and you got a 3s shell, and you got a 4s shell. And then you got a couple even shielding that will, although mainly we're talking about the entire, well actually no, shared electron would be the shielding there. But yeah, so you've got all these different energy levels that are shielding it, right? So even though, so it's bigger, it makes it way harder for to gain an electron. It's way easier to remove an electron from, or it's less likely to remove than, it's less likely to gain an electron than fluorine. It still wants to it still wants to gain an electron, but it's not as strong as something higher up. Does that make sense? So, yeah. So this one, therefore, atoms have a, I think I just put tighter here, and I put stronger. Or weaker, yeah, sorry. They have a weaker attraction for electrons. So, from left to right, does it increase or decrease? Increases, right? Why does it increase? They're becoming smaller, right? So that's a justification for it. Again, also the other way is, effective nuclear charge is getting bigger, a stronger charge that's acting on the same energy level, so all the electrons are held more tightly, and there's less, or there's more of an attraction for an extra electron. So increases. As we cross the periodic table from the side, therefore the elements have a stronger. I'm just going to fill this in because this is just a pretty simple blank, right? Because they're stronger or weaker. So with that being said, it's already in your notes though, but what would be the strongest, what would be the most active metal? Francium, right? Why is it francium?
It's the largest out of all the metals.
So it's the largest out of all the metals, right?
It's not the, it's, one of the largest.
It is the, right? Because, again, if we're looking at radius, right? If we go from, radius is always going to go here, and then radius is going to increase from top to bottom, right? So you go down here, in the bottom left corner, right? So I guess the only confusing part about this is just remember that technically, these are like, oh, these are lower, right? The lanthanide and actinide series, right? But remember, these are actually right here. They're filling in right here, just so we didn't have room for them in the periodic table, right? So in all actuality, francium is like the truest bottom left corner that you've got on the periodic table. So, what about fluorine? Why is it the most active nonmetal?
It's
Top right.
small, it's the top right, it's got the smallest, like,
Smallest radius, right? Yeah, so it's got the smallest radius, which
fused
means,
electrons.
yeah. So it's got the smallest radius, and it's got 7, which means it wants to gain an extra electron, right? So, what's the reason why these, the noble gases, technically they're more farther right, why would they not be reactive?
Complete shapes.
Full shell, full octet, right? Exactly. They have full octet, so they're not going to be reactive. Of course, that trim gets a little bit undermined when you get to like xenon and krypton, right? Because those, and if you remember that electronegativity chart, those have an electronegativity, but that's only because they're so big, and when they're bigger, there's a lot more room, wiggle room for stuff to happen. Right? So, with that out of the way, we do have a video that just kind of demonstrates the actual difference, right? Because they can say chemical activity all the time, but it's easier to show you what we're talking about for that. So let me switch it up here.
Screen down.
Yep. And this is one of the reasons, like again, we justify the reason why fluorine is the most active, which makes it very toxic.
Lithium, sodium, potassium, rubidium, cesium, and francium. They're all soft metals which can be cut with a knife. In air, the elements quickly become coated with compounds that form on the metal's surface. Here, for example, is lithium. When we slice it, you can see the metallic luster, but the black coating quickly reappears. Sodium is kept under oil to prevent reaction with air. Again, when we cut it, the metal surface can be seen.
Notice that the metals
This
are very
time,
soft.
corrosion occurs even more quickly. With the next alkali metal, potassium, the corrosion in air is so quick that it's hard to see the metallic luster at all.
So the oxygen stealing those
The
electrons
elements
super
seem to
fast.
react more quickly with air. Now let's see another reaction of the alkali metals, the reaction with water. We'll start with lithium. The metal floats on the water and reacts with it, giving off hydrogen gas. Now for sodium. The same sort of thing happens, although the reaction is a bit more vigorous.
And all they're doing is putting a piece of
All
metal into water.
will react with water in the same way. Let's see an equation for the reaction. Hydrogen gas is produced, and the metal dissolves to give an aqueous cation with a single positive charge.
That's kind of spoilers for the future. But you won't, when you do this electrometry, you won't use 1/2. That's just the
The heat
British way of
given
doing
out by the
things.
reaction is
That's
produced
just
so
an
quickly
excitement for
that the
now.
hydrogen gas catches fire. It burns with a line of flame. The next element is rubidium. This time, we put a safety screen between us and the reaction. You can see that things gradually become more terrifying as we go down the group. Let's try cesium, our fifth alkali metal.
Isn't
Okay.
cesium radioactive?
Listen at the very end when that cesium blows up. I can go for it.
Fifth alkali metal.
Listen very carefully at the end. You hear the whistle? That's the photographer or the director or something saying, "Oh wow, I wasn't expecting that." Wow, look what happened.
Yeah. Unfortunately, francium's not on that one. Is it in the full video?
No, you're never gonna have francium.
They never got francium? Yeah, okay. And so francium doesn't last too long. It's like, what is it, it's only like 2 grams?
22 minutes.
And so it's 22-minute half-life, so francium doesn't last long at all. But if they did have francium to work with, and they dropped it in the water, what do you think might happen?
Bigger explosion.
Bigger explosion, right? It would have been. I would not have wanted to be in that room unless I had like 3 sheets of like glass surrounding me, so I didn't get hit by it. And so that's just an example of how reactive things can get with chemical activity as you go down that route. And it's because, again, those electrons are way easier to remove when you go down the route. So it makes it way more reactive. I need to turn on the lights, that's fine. Same with, oh, that just ruined the projector. There you go, we're back. Same with fluorine, again, like I was saying, we mentioned earlier, that fluorine is like super toxic to humans, right? And so one of the reasons is because as a nonmetal, it's the most reactive nonmetal. So it wants to react with practically everything. And as an acid, we don't really, our body would not like that idea. That's why most of the time with fluorine, you have to keep it in, I believe it's just, you have to make sure you have special precautions when you store fluorine. I think you can store it in plastic. I can't remember off the top of my head. But you can't store it in glass. Like other acids you could potentially store in glass, fluorine is actually used to etch glass. Have you ever seen glass with like indents inside it? They use hydrofluoric acid. That's how reactive it is. You can just go through and melt glass. Yeah. So any questions on chemical activity? No? We're good? Sweet. So last up, oxidation state. So let's go ahead and quickly, I'll go ahead and quickly define oxidation state for you. It's the number of electrons an atom tends to gain, lose, or share to get a full octet. And so yeah, you basically just represent them with just how many you need to gain. If you're gaining electrons, it's going to be a negative number, right? Because you're gaining a negative charge. If you're losing electrons, you're getting a positive number because you're losing electrons, which means you have more positive of an ion that's made, right? And so that trend pretty much is pretty clear across the periodic table, right? So if we're talking about a halogen, for example, group 17, what would be the oxidation state on a halogen? -1. What about the chalcogens? -2, right? That's that group 16. I still have trouble pronouncing. What about alkali earth metals? +2, right? So yeah, and that's pretty much it. And so we can, it's useful because we can actually predict how some compounds are formed, if you combine two elements together, right? So let's say, for example, I'm going to combine, let's say I've got, let's do magnesium and fluorine. So I've got these two elements, I'm making a salt with them. How many magnesiums and how many, and so remember with compounds, they're always going to be neutral, right? With these, unless they're specifically like an ion, right? Like there are some polyatomic ions that you don't get to use as much right now, but like there's a whole list of them, polyatomic ions. But in general, if you make a compound, it's going to be a neutral compound. So how many, so let's do this one together, I guess. So first, let's start with magnesium. What's the oxidation state on magnesium?
+2.
+2, right? What's the oxidation state on fluorine? -1. So if I was going to create a formula for this compound, what do y'all think it might be?
Magnesium difluoride.
In magnesium difluoride, MgF2. That make sense? No, doesn't make sense? So I mean, it's basically all you're doing is looking at how much you need of each, right? If you've got +2, you've got to neutralize that +2 in order to get to a neutral atom, right? So I've got, if I'm combining magnesium and fluorine, fluorine's a -1, so all I've got to do is just add 2 fluorines, and that's how I make that compound. And that's it, with oxidation state.
Do one with, say, aluminum and oxygen.
Yeah, I was about to mention that, aluminum and oxygen. So let's start with aluminum and oxygen. Now this is a little bit more complicated, but let's start with aluminum first. What is the oxidation state for aluminum? Plus 3. What about for oxygen?
Maybe 2 aluminums and 3 oxygen.
You have what? 2 aluminums and 3 oxygens. How did you get? So you're saying Al2O3. How did you get that?
Because that would be 6 plus negative 6, which is 0, and that's what you have to.
It would be 6 plus negative 6 would be 0. Yeah, exactly. So another way you can do it also is just like, you basically, if you know these compounds are combining together, you look at these opposite charges and you're like, okay, I know that 2 can go here, and 3 can go here. And that's like the super quick way if you see an element like this, right? And the same way you could do that with magnesium and fluoride, right? So if we go back and just do the charges again, we go +1 and +2, -1 like we did earlier, right? And so you can use the exact same method here. And this is just like a quick draw way to just know instantly. So like, okay, there's -1 charge of fluorine, +2 charge here. We just need to cross them up, the numbers, and then we get MgFC. So is that the same method?
It's just like in math, lowest common multiple.
Yeah, lowest common multiple. So that's a super quick way to do these oxidation states. So if you ever see something like that, and you know that these 2 elements are going to be making a neutral compound together, all you got to do is look at oxidation states and see, okay, how is it going to work? How are they going to make this compound together? This is it is pretty easy to see on like these elements. It tends to be a little more useful when you deal with transition metals a lot, because transition metals, they can have multiple different oxidation states, which we don't go into right now. But like, let's see, like iron, for example, I think you can have a +2, +3, and a +4.
6.
That's a +6, excuse me. So you got a +2, +3, or +6 iron for iron, and which sounds really weird. And we'll get into, when you get into how metals bond, it'll make a little more sense, or how transition metals and metallic compounds bond within each other, it'll make a little more sense. But for instance like that, it's a little easy, it's a little better, because if you're combining a weird oxidation state with something that you know, it's very easy to just go back and be like, oh, okay, so I have these 2 oxidation states. They told me what oxidation state my transition metal was, and so all I gotta do is just the same thing, right? Yeah? Any questions?
What about magnesium and oxygen?
Magnesium and oxygen?
1 and
1 and 1, so what would be the formula there?
1.
MgO.
So just
And
MgO.
why not 2 and 2? If we did the crisscross.
It's like a fraction, like 2/2 is 1.
Right, you want the simplest ratio.
Yeah, simplest ratio, please.
So if you can reduce it like a fraction, you want to reduce it.
Does that make sense?
Did you guys do this like in 8th grade?
Yeah, that
You
makes
guys are
sense.
acting like you've seen this before, so that's good.
Yeah. Does that make sense for everybody, how these work? Okay. Awesome. And with that, that's the notes for the fill-in notes. Is there any parts on the fill-in notes that were confusing to y'all, anything that needs to be clarified? Or are y'all comfortable with what we talked about the last few days? Comfortable? Okay, so I did give you this sheet right here. Go ahead and try to draw arrows for that. Basically just a quick little map of the trends that you see, just a giant arrow there, and that'll make it a lot easier because again you can see it in person, and that way that knowledge is just always queued up for you. And then the only hard part is justifying why those trends happen. I'm going to go ahead and
Can
quickly.
we justify each one?
This is just putting the keys. Yes, this is just the keys. So I'm going to go ahead and quickly do that. And for like reactivity, you might also want to, like if you have a different color pin or a different way to write it, activity, that might be good because we know that metals and nonmetals react differently. affinity is going to be a little weird. So for electroaffinity, just put down which groups are the most negative or most favorable, and then which groups are the most positive or least favorable. There you go. And then put a little- okay. I'll get some of that real quick.
Who's keeping this for ourselves?
Yeah, so these are just for yourself. I'll put up a little P there. But this would be really nice, just as like a quick little like, oh, I just need to check out the trends again. Go down here, and it can be used for when you're studying too, because you could do something like, you quickly look at the trend and then justify the trend while you're like trying to study. And so that could be a good way to help you get in the habit of just recognizing it. It's weird because like this stuff it's memorization, but it's like it's not really memorization if you understand the trends, right? Because then it's like if you understand what's happening, then it's like the trends kind of just appear on their own. But this is a good way to help you study as well. So the only like mainly hard memorization stuff will be memorizing your terms, right? Just like knowing what electron affinity versus ionization energy is versus electronegativity. Which again, if you know those terms, you can link those terms to the periodic table, and then boom, your trends are done, right? You just finish up with your, or you're still working on it, yeah? One more. You got yours anyway? Okay. So I'll go ahead and quickly put mine up here then. Right? It's a little bit weird to see. So you can see for activity, I try to make two different ones. With metals, obviously, if we're going towards francium, I have arrows like this. Francium being the most active metal. Whereas for non-metals, I use dashed lines here. And then it goes up this way. I should have noted on here, and this is something that if you need to note down, I definitely suggest doing so. Is that like if you want to like do like most active metal versus non-metal, you can like make a box right here to denote that. Just for your own benefit there. Electronegativity, again, going up and to the right, going towards fluorine. I gotta slide this down. Yeah. Okay. Atomic mass, I had it to erase because I saw atomic mass and not, my brain was like atomic radius first when I was doing this, but with atomic mass, you know that's going to be increasing as you go from left to right and from top to bottom, because it's just the atomic mass, right? That's just how much it weighs.
Atomic radii, when it go left to right?
So yeah, the atomic radii is right below it. This is atomic mass on the second one. I got tricked too. So atomic mass, atomic radius. That makes sense? Yeah, sorry, when I saw that I was like, oh wait. But I guess it's just, that's more just like recognizing how your periodic table is generally structured, or how it's ordered. Ionization energy, up to the right, right? Atomic radii, to the left and down, like we were mentioning earlier, that's for atomic radius. And electron affinity, I was going to draw an arrow, but I thought it would be much easier to, you know, group 17, most favorable, most negative for electron affinity. Groups 2, 12, and 18, most positive, because they don't want to have an extra electron. Right? Do these all make sense? Awesome. So those are for you all to keep. And it'll be hopefully good study tools to help you while you're doing your study guide as well. And with that, we're done with everything I wanted to do today. So with the remaining time, I would go ahead and start working on the study guide. You have like about 7 or 8 minutes to do so. Just to go ahead and get a little bit of a head start there, because they're going to be doing, we'll be covering the study guide tomorrow in class. It's due Wednesday before the test, but if you have a good bit of it done, then when you watch the video, you can figure out any questions that you may have had on it. Yep. And those are posted. You posted the study guide, right? Up there? Yes, study guide is posted now, so you need to go ahead and pull up your Chromebooks and look at it together. All right? Cool.